Right now, almost everything in the universe is invisible to you, not hidden far away, invisible by nature. Every star, every galaxy, every planet, and every atom in your body adds up to less than 4% of what actually exists. The remaining 96% doesn't emit light, doesn't behave like normal matter, and doesn't fit comfortably into our understanding of reality. This isn't speculation. It's the conclusion forced on us by decades of precise measurements of how galaxies move, how the universe expands, and how gravity behaves when nothing visible should be there at all. In other words, most of reality is something we can't see, can't touch, and barely understand. The visible universe, every point of light you can see in the night sky, every distant galaxy photographed by the Hubble Space Telescope, every cosmic structure mapped by our most sophisticated instruments comprises what cosmologists call ordinary matter, or baryonic matter. This includes all the protons, neutrons, and electrons that form the familiar elements of the periodic table, from hydrogen to uranium. But recent observations by the Planck satellite and the Dark Energy Survey have revealed that this ordinary matter accounts for only 4.9% of the universe's total energy content. The remaining 95.1% consists of completely unknown substances that interact so weakly with ordinary matter that they remain essentially invisible to all our detection methods. 27% of the universe consists of dark matter, a mysterious substance that doesn't emit, absorb, or reflect electromagnetic radiation of any kind, making it completely invisible to telescopes. Yet this dark matter outweighs all visible matter by more than 5 to 1, creating the gravitational scaffolding that holds galaxies and galaxy clusters together. Even more mysterious is dark energy, which comprises approximately 68% of the universe's total energy content. This enigmatic force drives the accelerating expansion of space itself, pushing galaxies apart at ever-increasing rates, despite the gravitational attraction of all the matter they contain. Dr. Vera Rubin's pioneering research on galaxy rotation curves first revealed evidence for dark matter in the 1970s, showing that galaxies spin far too quickly to be held together by the gravity of their visible matter alone. Her observations suggested that each galaxy must be embedded in a massive halo of invisible matter that provides the additional gravity needed to prevent the galaxy from flying apart. The implications are staggering. When you look at the Milky Way galaxy stretching across the night sky, you're seeing only the tiny luminous fraction of a vast dark matter structure that extends far beyond the visible edges of the galaxy. The dark matter halo surrounding our galaxy has a mass roughly 10 times greater than all the visible stars, planets, and gas clouds combined. But dark matter is just the beginning of the mystery. The discovery of cosmic acceleration in 1998 by Saul Perlmutter's supernova cosmology project revealed that dark energy, an even more mysterious component, dominates the universe's energy budget and determines its ultimate fate. Dark energy appears to be a property of space itself, maintaining constant energy density even as space expands. As the universe grows larger, the total amount of dark energy increases proportionally, making its anti-gravitational effects stronger over time. This property ensures that cosmic expansion will continue accelerating forever, eventually carrying galaxies so far apart that future civilizations will see only empty darkness, where we now observe a universe filled with distant galaxies. Think about what this means for your understanding of reality. The chair you're sitting in, the air you're breathing, the planet beneath your feet, the star that lights your world. All of these familiar objects exist within a vast ocean of invisible substances that dwarf the visible universe in both mass and energy content. The dark matter streaming through your body right now carries no electromagnetic charge and interacts so weakly with ordinary matter that trillions of dark matter particles pass through every square centimeter of your body every second without leaving any trace of their passage. You are essentially transparent to dark matter, while dark matter is essentially invisible to you. Recent research suggests that the distinction between visible and dark components of the universe might reflect fundamental limitations in how matter and energy can interact rather than mere technological limitations in our detection capabilities. The universe might be constructed so that most of its content remains forever hidden from direct observation, detectable only through its gravitational effects on the small fraction of matter that can emit and absorb light. Dr. Sean Carroll's research on the cosmological constant suggests that dark energy might represent the energy density of empty space itself, the quantum vacuum energy that permeates all of reality. If this is correct, then the dark energy driving cosmic acceleration isn't a foreign substance, but rather a fundamental property of existence itself. This possibility transforms our understanding of what it means for space to be empty. The vacuum of space, which appears completely empty from our limited perspective, might actually be the most energetically significant component of reality, a seething ocean of quantum fields and vacuum fluctuations that determines the ultimate structure and evolution of the cosmos. As you contemplate the night sky, remember that you're seeing only the luminous tracery of a cosmic iceberg whose bulk remains completely hidden. The universe you inhabit is far larger, stranger, and more mysterious than the portion revealed to your senses and instruments. Tonight, we're going to explore the most profound mystery in modern cosmology, the hidden 96% of reality that surrounds us, invisibly shapes cosmic evolution from behind the scenes, and challenges our most basic assumptions about the nature of existence itself. If you're fascinated by the hidden architecture of reality, subscribe and hit the thumbs up button. And here is a mind-bending question to consider. If you could choose to see dark matter and dark energy directly, but doing so would make ordinary matter invisible to you, would you make that trade? Comment your reasoning below. I'll pin the most thought-provoking answer. What we're about to discover will fundamentally change how you think about the space around you, the cosmic forces shaping reality, and the humbling possibility that everything we can observe and understand represents just the tiniest visible surface of a cosmic reality so vast and strange that it might be forever beyond human comprehension. Consider this. The universe might be constructed so that conscious observers like us can only directly perceive the small fraction of reality that is capable of complex organization and information processing. The invisible 96% might be forever hidden not because of technological limitations, but because the nature of consciousness itself requires interaction with the organized electromagnetic matter that represents only reality's visible surface. Now let's begin our journey into the cosmic dark, where we'll discover that the universe you think you know is just a thin film of light, floating on an ocean of invisible mystery whose depths may be infinite. Chapter 1. Hidden Reality, the Reality. First thing you need to understand about the hidden 96% of the universe is that we're not dealing with some exotic frontier of theoretical physics that might be discovered in the distant future. We're surrounded by invisible reality right now at this very moment, in quantities so vast that they dwarf everything visible by ratios that challenge human comprehension. The dark matter and dark energy that comprise the hidden universe aren't abstract concepts. They're the dominant components of the reality you inhabit, shaping every aspect of cosmic structure from the largest scales down to the space between galaxies. The evidence for this hidden reality comes from multiple independent lines of observation that all point to the same shocking conclusion. The universe contains far more matter and energy than we can directly detect. These aren't theoretical predictions, but observational facts confirmed by dozens of different measurement techniques across multiple decades of precision cosmology. Dr. Fritz Zwicky first discovered evidence for hidden matter in 1933 while studying the Coma galaxy cluster. His observations showed that individual galaxies within the cluster were moving much too fast to be gravitationally bound by the visible matter he could observe. The cluster should have dispersed long ago, unless it contained roughly 10 times more matter than was visible through telescopes. Zwicky called this invisible matter, dunkel materie, dark matter, and his calculations suggested that the universe contained vast amounts of gravitating matter that emitted no light. For decades, astronomers hoped that improved telescopes and detection methods would reveal this missing matter in the form of dim stars, gas clouds, or other conventional astronomical objects. Instead, every technological advance and observational improvement has confirmed that the missing matter isn't dim or distant. It is fundamentally different from ordinary matter, interacting through gravity while remaining completely invisible to electromagnetic radiation across all wavelengths from radio waves to gamma rays. The gravitational effects of this dark matter are unmistakable when you examine the rotation curves of spiral galaxies. Dr. Vera Rubin's pioneering observations in the 1970s showed that stars in the outer regions of galaxies orbit at nearly constant speeds rather than the declining speeds predicted by Newton's laws if only visible matter provided the gravitational force. These flat rotation curves require dark matter halos that extend far beyond the visible edges of galaxies, with masses typically 5 to 10 times greater than all the visible stars and gas combined. The dark matter forms a vast spherical halo surrounding each galaxy, creating the gravitational wells within which ordinary matter can condense to form stars and planetary systems. Recent computer simulations of cosmic structure formation show that without dark matter, galaxies as we know them could never have formed. The gravitational attraction of ordinary matter alone would be insufficient to overcome the expansion of space and pull together the dense concentrations of matter necessary to ignite star formation on galactic scales. Dr. Carlos Frank's research on cold dark matter cosmology demonstrates that dark matter must have begun clumping together very early in cosmic history, when the universe was still too hot for ordinary matter to form neutral atoms. These early dark matter structures created the gravitational scaffolding that later guided ordinary matter into the cosmic web of filaments and voids we observe today. The cosmic microwave background radiation provides additional evidence for dark matter through precise measurements of temperature fluctuations that reflect the cosmic conditions, approximately 380,000 years after the Big Bang. The WMAP and Planck satellites have mapped these fluctuations with extraordinary precision, revealing acoustic oscillations in the primordial plasma that can only be explained if dark matter comprises approximately 27% of the universe's total energy content. These cosmic microwave background observations also provide the first direct evidence for dark energy through measurements of cosmic geometry and expansion history. The universe appears to be geometrically flat, which requires a total energy density very close to the critical density needed to balance cosmic expansion against gravitational collapse. But when astronomers add up all the matter they can observe, both ordinary matter and dark matter inferred from gravitational effects, the total comes to only about 32% of the critical density. The remaining 68% must consist of some form of energy that doesn't clump gravitationally like matter, but instead maintains constant density as space expands. This dark energy component was confirmed through observations of distant Type Ia supernova by the Supernova Cosmology Project and the High-Z Supernova Search Team. These observations, which earned the 2011 Nobel Prize in Physics, showed that cosmic expansion has been accelerating for the past several billion years rather than slowing down as expected if matter and gravity dominated cosmic dynamics. Dr. Adam Rees's precision measurements of supernova distances and redshifts demonstrate that dark energy began dominating cosmic expansion approximately 7 billion years ago, when the universe had expanded enough that matter density decreased below the threshold where dark energy effects become significant. The mathematical framework describing this hidden reality comes from Einstein's general theory of relativity, which relates the geometry and expansion of spacetime to its total energy and matter content through the Friedmann equations. These equations successfully predict cosmic expansion history when dark matter and dark energy are included, but fail completely when only ordinary matter is considered. Recent observations from gravitational lensing surveys provide independent confirmation of dark matter's existence and distribution throughout the universe. When light from distant galaxies passes through regions of space containing dark matter concentrations, the gravitational effects of the dark matter bend the light paths and distort the images of background galaxies. Dr. Richard Massey's analysis of weak lensing data from the Hubble Space Telescope and large ground-based surveys has created detailed maps showing how dark matter is distributed throughout the cosmic web. These maps reveal dark matter filaments connecting galaxy clusters, creating a vast network of invisible structure that underlies all visible cosmic architecture. The bullet cluster observations provide perhaps the most direct evidence for dark matter as a distinct substance rather than a modification of gravitational laws. When two galaxy clusters collide, the ordinary matter in the form of hot gas experiences friction and slows down, while the dark matter passes through unimpeded because it interacts only through gravity. Dr. Douglas Clowe's analysis of the bullet cluster collision shows clear spatial separation between the visible matter, traced by X-ray emission from hot gas, and the gravitational mass, traced by weak lensing effects. This separation can only be explained if most of the gravitational mass consists of collisionless, dark matter particles that do not interact electromagnetically. Recent results from underground dark matter detection experiments have set increasingly stringent limits on how dark matter might interact with ordinary matter through non-gravitational forces. Despite years of searching with ever more sensitive detectors, no direct detection of dark matter particles has been achieved, suggesting that these particles interact extraordinarily weakly with ordinary matter. The Large Hadron Collider at CERN has searched for dark matter particles that might be produced in high-energy collisions, but so far has found no evidence for the production of stable, long-lived particles that could account for cosmic dark matter. This absence of detection suggests that dark matter particles, if they exist, have masses and interaction strengths very different from ordinary matter particles. Alternative theories propose that apparent dark matter effects might result from modifications to Einstein's gravity laws rather than from invisible matter. Modified Newtonian dynamics, MOND, and other alternative gravity theories can explain galaxy rotation curves without invoking dark matter, but they struggle to account for the full range of cosmological observations, particularly the cosmic microwave background and gravitational lensing data. The profound implications of hidden reality extend beyond academic cosmology to challenge our most basic assumptions about the nature of existence itself. If 96% of the universe consists of substances that we cannot directly observe or interact with, then our entire scientific understanding of reality is based on studying a tiny, potentially unrepresentative sample of cosmic matter and energy. Dr. Sean Carroll's research on the foundations of cosmology suggests that the hidden components of the universe might represent fundamentally different types of physical reality rather than just exotic forms of familiar matter and energy. Dark matter and dark energy might operate according to physical laws and principles that are completely inaccessible to beings composed of ordinary matter. This possibility raises profound questions about the relationship between consciousness and reality. If consciousness depends on the complex electromagnetic interactions possible with ordinary matter, then conscious observers might be forever limited to perceiving and understanding only the tiny fraction of reality that can participate in electromagnetic processes. As we prepare to explore the specific nature of dark matter and its role in shaping cosmic structure, remember that you are currently embedded within and surrounded by a hidden reality so vast that it makes the visible universe seem like a few fireflies flickering in an ocean of cosmic darkness. Chapter 2. Dark Matter. In the vast darkness between galaxies, an invisible cosmic web stretches across hundreds of millions of light years, composed of a substance so alien to our everyday experience that it interacts with ordinary matter almost exclusively through gravity. Yet this strange material provides the structural foundation for every galaxy, every star, and ultimately every planet capable of supporting life. Dark matter isn't just a mysterious component of the cosmos. It is the hidden architect that makes the visible universe possible. Dark matter particles stream through your body at this very moment. Billions upon billions of them passing through every square centimeter of space every second, carrying no electric charge, absorbing no light, emitting no radiation, yet collectively outweighing all the visible stars in the observable universe by more than 5 to 1. You are essentially transparent to dark matter, while dark matter is essentially invisible to you, creating a ghostly parallel reality that coexists with ordinary matter while remaining forever hidden from direct observation. The nature of dark matter represents one of the deepest mysteries in modern physics. Unlike ordinary matter, which is composed of protons, neutrons, and electrons that interact through electromagnetic, strong nuclear, and weak nuclear forces, dark matter appears to interact only through gravity and possibly the weak nuclear force. This makes dark matter particles extraordinarily difficult to detect despite their cosmic abundance. Dr. Gerard 't Hooft's research on particle physics suggests that dark matter might consist of entirely new types of fundamental particles that were predicted by supersymmetry theories but have never been observed in particle accelerators. These hypothetical particles, called WIMPs, weakly interacting massive particles, would have masses typically 10 to 1,000 times greater than protons, but interaction cross-sections so small that they rarely collide with ordinary matter. Recent calculations by Dr. Dan Hooper at Fermilab show that if dark matter consists of WIMPs with the properties predicted by supersymmetry, approximately 10 million dark matter particles pass through your body every second, but the probability of any individual particle interacting with your atoms is so small that you might experience only one dark matter collision in your entire lifetime. This extraordinary weakness of dark matter interactions explains why dark matter can form the large-scale structure of the universe while remaining invisible to telescopes. Dark matter responds to gravity just like ordinary matter, allowing it to clump together under its own gravitational attraction. But because dark matter particles rarely collide with each other or with ordinary matter, dark matter structures can interpenetrate and form complex hierarchical patterns that would be impossible for ordinary matter. Computer simulations of cosmic structure formation, such as the Millennium simulation conducted by the Max Planck Institute for Astrophysics, reveal that dark matter naturally organizes itself into a cosmic web of filaments, nodes, and voids that spans the entire observable universe. This web provides the gravitational scaffolding that guides ordinary matter into galaxies and galaxy clusters. Dr. Volker Sprengel's analysis of these simulations shows that dark matter halos form through a process called hierarchical clustering, where smaller dark matter clumps merge together over billions of years to create increasingly large structures. The largest dark matter halos can contain thousands of times more mass than the visible components of the galaxy clusters they surround. The distribution of dark matter within individual galaxies follows remarkably consistent patterns across different galaxy types and masses. Observations of galaxy rotation curves show that dark matter density typically peaks near galaxy centers and decreases smoothly with distance, creating roughly spherical halos that extend far beyond the visible edges of galaxies. Dr. Julio Navarro's research on dark matter halo profiles demonstrates that these density distributions follow a universal mathematical relationship known as the NFW profile, regardless of galaxy mass or formation history. This universality suggests the dark matter halo formation is governed by fundamental physical processes that operate similarly throughout the cosmos. Recent gravitational lensing observations provide direct evidence for the three-dimensional structure of dark matter distributions. When light from distant galaxies passes through regions of space containing dark matter concentrations, the gravitational effects of the dark matter bend the light paths and create distorted images of the background galaxies. Dr. Richard Massey's analysis of weak lensing data from the Cosmic Evolution Survey, COSMOS, has created detailed, three-dimensional maps of dark matter distribution covering billions of light-years of space. These maps reveal dark matter filaments connecting galaxy clusters and show how dark matter structure has evolved over cosmic time as the universe expanded and galaxies formed. The interaction between dark matter and ordinary matter during galaxy formation creates observable consequences that provide additional evidence for dark matter's existence and properties. When ordinary matter falls into dark matter potential wells, it heats up through gravitational compression and can form stars at rates determined by the depth and profile of the dark matter halo. Dr. Alison Brooks' research on galaxy formation simulations shows that the star formation histories of galaxies depend critically on their dark matter environment. Galaxies in massive dark matter halos tend to form stars early and intensely, while galaxies in smaller halos have more extended star formation periods. These predictions match observations of galaxy stellar populations and ages. The cosmic microwave background radiation provides additional constraints on dark matter properties through precise measurements of acoustic oscillations in the primordial plasma. These oscillations were driven by the interplay between gravity, radiation pressure, and the different behavior of dark matter and ordinary matter before cosmic recombination. Dr. Wayne, whose analysis of cosmic microwave background data shows that dark matter began clustering gravitationally, while ordinary matter remained coupled to radiation and could not yet form neutral atoms. This early clustering by dark matter created the initial density fluctuations that later grew into the cosmic web structure we observe today. Recent observations of galaxy collisions provide some of the most direct evidence for dark matter as a distinct substance rather than a modification of gravitational laws. During collision events like the bullet cluster, ordinary matter in the form of hot intracluster gas experiences friction and electromagnetic interactions that slow its motion, while dark matter passes through collision regions essentially unimpeded. Dr. Marusa Braddock's analysis of multiple cluster collision systems shows systematic spatial offsets between the distributions of ordinary matter traced by X-ray emission and gravitational mass traced by weak lensing. These offsets can only be explained if most of the gravitational mass consists of collision-less dark matter that doesn't interact electromagnetically. The search for dark matter particles through direct detection experiments has become one of the most intensive research programs in modern physics. Underground laboratories around the world operate increasingly sensitive detectors designed to catch the rare occasions when dark matter particles might interact with atomic nuclei in carefully shielded detector materials. Dr. Elena April's Xenon collaboration operates liquid xenon detectors deep underground in Italy, shielded from cosmic radiation and other background sources that could mimic dark matter signals. Despite years of operation with ever-improving sensitivity, these experiments have detected no confirmed dark matter interactions, placing increasingly stringent limits on dark matter particle properties. Alternative dark matter candidates include Axions hypothetical particles predicted by theories that solve problems in quantum chromodynamics. Axions would have extremely small masses and interact so weakly with ordinary matter that they would be nearly impossible to detect directly, but they might be detectable through their conversion to photons in strong magnetic fields. Dr. Pierre Saikovic's research on axion detection has led to experiments like a DMX, Axion Dark Matter Experiment, that searched for the conversion of dark matter axions into microwave photons within powerful magnetic fields. These experiments have not yet detected axions, but have ruled out certain ranges of axion masses and interaction strengths. Primordial black holes represent another potential dark matter candidate. These hypothetical objects would have formed from density fluctuations in the early universe rather than from stellar collapse, and they could have masses ranging from microscopic scales to many solar masses. If primordial black holes comprise dark matter, they would interact gravitationally, but remain invisible unless they occasionally consume ordinary matter and produce detectable radiation. Recent observations by LIGO gravitational wave detectors have detected mergers of black hole pairs with masses in the range where primordial black holes might exist, but the observed merger rate is too low to account for all dark matter, unless primordial black holes have very specific mass distributions and clustering properties. The implications of dark matter extend far beyond astronomy and cosmology to fundamental questions about the nature of matter and energy in the universe. If dark matter particles exist, they represent entirely new categories of matter governed by physical laws and interaction principles that remain largely unknown to current science. Dr. Lisa Randall's research on dark matter models suggests that dark matter might exist in its own dark sector with its own forces, particles, and possibly even complex chemistry analogous to but completely separate from ordinary matter chemistry. This dark sector might contain dark atoms, dark molecules, and even dark stars composed entirely of dark matter. From this perspective, the universe might contain two parallel realities: the ordinary matter reality we observe and interact with, and a dark matter reality that coexists in the same space, but operates according to different physical principles. These two realities would interact only through gravity, remaining otherwise completely isolated from each other. As we prepare to explore how dark matter creates the invisible scaffolding for cosmic structure, remember that you are currently surrounded by and embedded within a vast dark matter halo whose mass dwarfs everything visible in our galaxy, yet remains as invisible to you as you are irrelevant to its alien physics. Chapter 3: Invisible Scaffolding Stretching across the cosmic void for hundreds of millions of light years lies an invisible architectural framework so vast and precisely organized that it dwarfs any structure ever conceived by human imagination. A Prokinish and threatened imagination, a cosmic scaffolding built from dark matter filaments that guides the formation of every galaxy, every star cluster, and every cosmic structure visible in the universe today. This hidden framework doesn't just support visible matter. It defines the very shape and organization of reality on the largest scales, creating a blueprint for cosmic structure that operates entirely behind the scenes of observable astronomy. The invisible scaffolding of dark matter operates like a vast three-dimensional spiderweb spanning the entire observable universe. At the intersections of dark matter filaments, where multiple streams of invisible matter converge, the gravitational wells become deep enough to trap ordinary matter and compress it until stars begin to form. These intersection points become the locations of galaxies and galaxy clusters, while the vast spaces between filaments remain nearly empty of both dark and ordinary matter. Dr. Jupe Shea's research using the Eagle cosmological simulation reveals how this scaffolding develops over cosmic time. In the early universe, tiny quantum fluctuations in dark matter density grew under their own gravitational attraction, forming an intricate network of collapsing filaments that stretched across space. As the universe expanded, these filaments became increasingly defined, creating a cosmic web structure that determines where galaxies can form and how they cluster together. The mathematics describing this invisible scaffolding come from gravitational instability theory, developed by Sir James Jeans in the early 20th century. According to this theory, any region of space with slightly higher than average matter density will experience stronger gravitational attraction, causing it to pull in surrounding matter and grow denser over time. This process creates a runaway effect where dense regions become denser while sparse regions become emptier. For dark matter, this gravitational instability process can operate unimpeded by electromagnetic forces, radiation pressure, or other effects that resist the collapse of ordinary matter. Dark matter can begin clustering immediately after the Big Bang, creating the foundation for all subsequent structure formation in the universe. Recent observations from the Dark Energy Survey and the Kilo-degree Survey have mapped the invisible scaffolding through weak gravitational lensing measurements that reveal how dark matter is distributed throughout the cosmic web. When light from distant galaxies passes through regions of space containing dark matter filaments, the gravitational effects of the dark matter bend the light paths and create subtle distortions in the shapes of background galaxies. Dr. Catherine Hayman's analysis of weak lensing data has created detailed maps of dark matter distribution covering thousands of square degrees of sky and extending billions of light years into space. These maps reveal dark matter filaments connecting galaxy clusters, creating a network of invisible highways along which ordinary matter flows to fuel galaxy formation. The scale of this invisible scaffolding is difficult to comprehend. Individual dark matter filaments can stretch for hundreds of millions of light years while containing trillions of times more mass than our entire solar system. The largest dark matter structures, called cosmic walls or sheets, can extend for over 1 billion light years and contain millions of galaxy groups connected by a network of dark matter bridges. Computer simulations like the Millennium Simulation and the Illustris project show how galaxy formation follows the contours of this invisible scaffolding. Ordinary matter flows along dark matter filaments like water flowing through underground cave systems, accumulating at intersection points where multiple filaments meet. These intersection points become the sites of intense star formation and galaxy assembly. Dr. Mark Vogelsberger's research on the Illustris simulation demonstrates that galaxy properties depend critically on their location within the dark matter scaffolding. Galaxies that form at the centers of massive dark matter halos tend to be large, elliptical, and red, having exhausted their gas supplies through intense early star formation. Galaxies that form along dark matter filaments tend to be smaller, spiral-shaped, and blue, continuing to form stars as they accrete gas from their surroundings. The invisible scaffolding also determines the large-scale velocity flows of galaxies through space. Galaxies don't move randomly through the universe, but instead follow the gravitational influences of the dark matter distribution, flowing along dark matter filaments toward regions of higher dark matter density. Recent measurements of galaxy peculiar velocities by the 6DF Galaxy Survey and other projects reveal these cosmic flows extending across hundreds of millions of light years. Entire galaxy clusters are flowing toward regions of space called great attractors, where particularly massive concentrations of dark matter create gravitational wells deep enough to influence galactic motions across vast distances. The Laniakea supercluster, identified by Dr. Brent Tully's analysis of galaxy velocity flows, represents one such region where hundreds of galaxy groups are flowing along dark matter streams toward a common gravitational center. Our Milky Way galaxy participates in this cosmic flow, moving at approximately 600 kilometers per second relative to the cosmic microwave background radiation. The invisible scaffolding operates at multiple scales, simultaneously creating a hierarchical structure where smaller dark matter halos exist within larger ones in a pattern that extends from galaxy-scale halos containing YP solar masses up to cosmic web filaments containing 1016 solar masses or more. Dr. Risa Wexler's research on dark matter halo assembly shows that this hierarchical structure forms through a process called hierarchical clustering, where smaller halos merge together over cosmic time to create progressively larger structures. The merger histories of dark matter halos determine the formation histories of the galaxies they contain, influencing everything from stellar populations to black hole masses. The cosmic web structure created by dark matter scaffolding contains vast empty regions called cosmic voids that can span hundreds of millions of light years with very little matter of any kind. These voids aren't truly empty, but contain dark matter densities much lower than the cosmic average, creating regions where galaxy formation is strongly suppressed. Dr. Rien van de Wegaard's research on cosmic voids reveals that these empty regions play an important role in cosmic structure formation by providing the contrast that makes dense regions appear dense by comparison. The existence of large voids helps drive the formation of dense filaments and cluster nodes by providing regions from which matter can be drawn during gravitational collapse. The invisible scaffolding also influences cosmic evolution on the largest scales through its effects on dark energy and cosmic expansion. As dark matter structure grows over time, it creates increasingly deep gravitational wells that can slow down cosmic expansion locally, while dark energy continues to accelerate expansion in regions with low matter density. Recent observations suggest that this interplay between dark matter clustering and dark energy expansion creates spatial variations in cosmic expansion rates. Regions of space containing dense dark matter concentrations expand more slowly than regions dominated by dark energy, creating a complex pattern of expansion that varies depending on local dark matter density. The formation of cosmic structure through dark matter scaffolding represents one of the most successful predictions of the standard cosmological model. Observations of galaxy clustering, cosmic microwave background fluctuations, and gravitational lensing all confirm the theoretical predictions for how structure should form in a universe dominated by dark matter and dark energy. Dr. Carlos Frank's comparison between cosmological simulations and observational data shows remarkable agreement across a wide range of scales and cosmic epochs. The invisible scaffolding predicted by cold dark matter theory matches the observed distribution of galaxies and galaxy clusters with extraordinary precision, providing strong evidence that our understanding of dark matter structure formation is fundamentally correct. However, the invisible scaffolding also creates several puzzles that challenge our understanding of dark matter physics. Simulations predict that dark matter halos should contain many more small satellite structures than are observed around galaxies like the Milky Way. This missing satellites problem suggests that either our understanding of dark matter is incomplete or that galaxy formation processes are more complex than current models assume. Recent research on warm dark matter and self-interacting dark matter explores whether modifications to dark matter properties could resolve these small-scale structure problems while preserving the successful predictions of cold dark matter on larger scales. These alternative dark matter models predict subtle differences in the structure of dark matter halos that might be detectable through improved observations. The invisible scaffolding of dark matter represents perhaps the most profound example of hidden reality shaping visible phenomena. Every galaxy you can see through telescopes, every star formation region, every cosmic structure mapped by astronomical surveys exists only because invisible dark matter created the gravitational framework necessary for ordinary matter to condense and organize into complex structures. Without this invisible scaffolding, the universe would be a smooth, featureless expanse of hydrogen and helium gas, slowly expanding into ever greater emptiness. No galaxies would form, no stars would ignite, no planets would condense, and no conscious observers would exist to contemplate the hidden architecture that makes complex cosmic structure possible. As we prepare to explore dark energy and its role in accelerating cosmic expansion, remember that the scaffolding supporting everything visible in the universe remains forever invisible, detectable only through its gravitational influences on the small fraction of cosmic matter that can emit and absorb light. Chapter 4. Dark Energy. permeating every cubic centimeter of space throughout the observable universe, including the space between your atoms and the space between distant galaxies, exists a mysterious energy field so powerful that it drives the accelerating expansion of space itself, yet so subtle that it remained undetected until the final years of the 20th century. This dark energy represents the most abundant form of energy in the cosmos, comprising approximately 68% of everything that exists. Yet it operates according to principles so alien to our everyday experience that it challenges our most fundamental understanding of what energy actually means. Dark energy possesses a property that distinguishes it from every other known form of matter or energy. As space expands and its volume increases, the amount of dark energy in the universe increases proportionally, maintaining constant energy density throughout cosmic expansion. This behavior is exactly opposite to ordinary matter and radiation, which become less dense as space expands, suggesting that dark energy might be a fundamental property of spacetime itself rather than a substance that exists within space. The discovery of dark energy emerged from one of the most ambitious observational programs in the history of astronomy, the systematic study of type Ia supernova in distant galaxies, conducted by two competing research teams in the 1990s. Dr. Saul Perlmutter's Supernova Cosmology Project and Dr. Adam Rees' S-High-Z Supernova search team both reached the same shocking conclusion. The expansion of the universe is not slowing down under the influence of gravity as expected, but instead accelerating at an ever-increasing rate. Type Ia supernova serve as standard candles for measuring cosmic distances because they result from the complete destruction of white dwarf stars that reach a consistent maximum mass before exploding. The intrinsic brightness of these explosions is remarkably uniform, allowing astronomers to determine the distance to host galaxies by comparing observed brightness to the known intrinsic luminosity. Dr. Brian Schmidt's analysis of the supernova data revealed that distant galaxies appear dimmer than expected for their redshifts, indicating that they are farther away than predicted by models of a universe where expansion was slowing down. This observation can only be explained if cosmic expansion has been accelerating for approximately the past 7 billion years, driven by some form of energy that counteracts gravitational attraction. The mathematical framework describing dark energy comes from Einstein's general theory of relativity, specifically the cosmological constant term that Einstein originally introduced to allow for a static universe. Einstein later called this cosmological constant his greatest mistake when Hubble discovered cosmic expansion, but modern observations suggest that something very much like Einstein's cosmological constant is indeed driving current cosmic acceleration. The cosmological constant represents the energy density of empty space itself, the quantum vacuum energy that permeates all of reality. Quantum field theory predicts that empty space should contain energy due to quantum fluctuations of virtual particle pairs that constantly appear and disappear on timescales allowed by the uncertainty principle. However, when physicists calculate the expected energy density of quantum vacuum fluctuations, they obtain a value that is approximately 10,120 times larger than the dark energy density inferred from cosmological observations. This enormous discrepancy, known as the cosmological constant problem, represents one of the most profound failures of theoretical physics to match observational reality. Dr. Steven Weinberg's research on the cosmological constant problem suggests that the dark energy density must be precisely fine-tuned to allow the formation of cosmic structure. If dark energy were much stronger, cosmic expansion would accelerate so rapidly that gravitational attraction could never overcome expansion to form galaxies and stars. If dark energy were much weaker or absent entirely, the universe might recollapse before life could evolve. Recent observations from the Dark Energy Survey and the Baryon Oscillation Spectroscopic Survey have measured the equation of state parameter for dark energy with increasing precision. This parameter, called W, describes how dark energy density changes as the universe expands. For Einstein's cosmological constant, W equals exactly -1, while other dark energy models predict slightly different values. Current measurements indicate that W is very close to -1, consistent with a true cosmological constant. But the uncertainty in these measurements still allows for slowly evolving dark energy fields called quintessence. Quintessence models propose that dark energy consists of a slowly rolling scalar field, similar to the inflation field that drove exponential expansion in the early universe. Dr. Paul Steinhardt's research on quintessence suggests that dark energy might be dynamic rather than constant, potentially changing its properties over cosmic time. If dark energy is evolving, it might eventually decay or change sign, leading to different cosmic futures than predicted by a constant dark energy component. The effects of dark energy extend beyond cosmic expansion to influence the formation and evolution of cosmic structure. As dark energy becomes more dominant over time, it begins to halt the collapse of dark matter structures and prevents the formation of new galaxy clusters. This creates a cosmic epoch transition from structure growth dominated by gravity to structure stagnation dominated by dark energy. Dr. Michael Turner's analysis of cosmic structure formation shows that dark energy began dominating cosmic expansion approximately 7 billion years ago, when the universe had expanded enough that matter density decreased below the threshold where dark energy effects become significant. Before this transition, gravity dominated and cosmic structure continued growing rapidly. After this transition, structure growth slowed dramatically and will eventually stop entirely. Recent computer simulations of cosmic evolution, including dark energy effects, predict that galaxy cluster formation essentially ceases in the current cosmic epoch. The massive galaxy clusters we observe today represent the final generation of major gravitational structures that will ever form in our universe. Future cosmic evolution will be dominated by the dispersal of existing structures as dark energy drives accelerating expansion. The nature of dark energy remains one of the deepest mysteries in physics, with several competing theoretical explanations. Modified gravity theories propose that apparent dark energy effects result from deviations from Einstein's general relativity on cosmic scales rather than from a new energy component filling space. Dr. Sean Carroll's research on modified gravity alternatives to dark energy includes scenarios where gravity becomes weaker on very large scales, creating apparent acceleration without requiring any new energy fields. However, these modified gravity theories must explain not only cosmic acceleration, but also the full range of cosmological observations, including cosmic microwave background anisotropies and gravitational lensing effects. Extra-dimensional physics provides another potential explanation for dark energy through mechanisms where our familiar three-dimensional space exists as a brane embedded in higher dimensional space. Dark energy might represent the influence of gravitational fields or energy sources that exist in extra dimensions but affect our three-dimensional space through geometric effects. Dr. Lisa Randall's research on brand-new old cosmology shows how energy and matter in extra dimensions could influence cosmic expansion in our three-dimensional space without being directly detectable through electromagnetic interactions. From this perspective, dark energy might be evidence for physics beyond the familiar four dimensions of spacetime. The anthropic principle provides another perspective on dark energy by noting that the observed dark energy density falls within the narrow range that allows cosmic structure formation and stellar evolution to proceed. Dr. Steven Weinberg's anthropic analysis suggests that we might observe precisely the dark energy density that makes life possible, regardless of what fundamental physics predicts for vacuum energy. Multiverse theories propose that our universe is one of many, each with different values of physical constants, including the dark energy density. Only universes with dark energy densities in the narrow range compatible with structure formation would develop conscious observers capable of measuring dark energy. From this anthropic perspective, the apparent fine-tuning of dark energy density isn't surprising but inevitable. Recent observations from gravitational wave detectors provide new ways to study dark energy through precision measurements of cosmic expansion at different epochs. When gravitational waves from distant sources travel through expanding space, their wavelengths are stretched by cosmic expansion in ways that depend on the dark energy density and its evolution over time. Dr. Daniel Holtz's research on using gravitational waves as standard sirens for cosmology shows that future gravitational wave observations could provide independent measurements of cosmic expansion history with precision comparable to or better than current supernova and cosmic microwave background observations. The implications of dark energy extend far beyond cosmology to fundamental questions about the nature of space, time, and energy itself. If dark energy represents the energy of empty space, then the vacuum contains vastly more energy than any other component of reality, making vacuum energy the dominant player in cosmic evolution. This possibility transforms our understanding of what it means for space to be empty. Rather than nothingness, empty space might be the most energetically significant aspect of reality, a quantum field system so rich and complex that it determines the ultimate fate of the entire universe. As we prepare to explore how dark energy drives cosmic acceleration and shapes the universe's ultimate destiny, remember that the dark energy field permeating the space around you right now is not just an exotic curiosity, but the most powerful force in nature, ultimately responsible for carrying every galaxy in the observable universe toward a cold, dark and lonely future where the cosmos expands into infinite emptiness. Chapter 5. Cosmic Acceleration. At this very moment, space itself is expanding at an accelerating rate so profound that distant galaxies are racing away from us at speeds approaching the speed of light, carried by the stretching of space-time itself rather than by their motion through space. This cosmic acceleration, driven by the mysterious dark energy that permeates every corner of the universe, represents the most dramatic large-scale phenomenon in nature, a runaway expansion process that will ultimately determine the fate of every star, every galaxy, and every possible form of life in the cosmos. The acceleration of cosmic expansion means that the universe's expansion rate is not constant but increasing over time. The Hubble constant, which measures how quickly distant galaxies recede from us, was larger in the past when the universe was smaller and will be larger in the future as dark energy becomes increasingly dominant over matter and radiation. Dr. Adam Rees's Nobel Prize-winning measurements of distant supernova revealed that galaxies at redshift z equals 0.5, corresponding to light that has traveled for approximately 5 billion years, appear significantly dimmer than expected for a universe expanding at constant rate. This dimming indicates that these galaxies are farther away than predicted, possible only if cosmic expansion was slower in the past and has accelerated since then. The mathematics of cosmic acceleration come from the Friedmann equations, which relate the expansion rate of the universe to its energy and matter content through Einstein's general theory of relativity. For ordinary matter and radiation, gravity acts to slow cosmic expansion over time. For dark energy with negative pressure, the gravitational effect is repulsive, causing expansion to accelerate rather than decelerate. Recent precision measurements from the Planck satellite constrain the current expansion rate to h equals 67.4 kilometers per second, MPC. The transition from decelerated to accelerated expansion occurred when the universe was roughly half its current age. Before this transition, ordinary matter and dark matter provided enough gravitational attraction to slow cosmic expansion despite the presence of dark energy. As the universe expanded and matter density decreased, Dark energy's repulsive effects eventually overcame matter's attractive effects, initiating the current epoch of accelerated expansion. Dr. Sean Carroll's analysis of cosmic expansion history shows that this transition represents a fundamental change in cosmic dynamics. The early universe was dominated by radiation, then matter, and now dark energy. Each epoch transition has dramatically altered the rate of cosmic evolution and the types of physical processes that can occur on cosmic scales. The acceleration of cosmic expansion has profound implications for the formation and evolution of cosmic structure. As expansion accelerates, it becomes increasingly difficult for gravity to overcome the stretching of space and pull matter together to form new gravitational structures like galaxy clusters. Recent computer simulations by Dr. Volker Springel and collaborators show that galaxy cluster formation essentially ceases in the current epoch of accelerated expansion. The massive galaxy clusters we observe today represent the final generation of major gravitational structures that will form in our universe. Future cosmic evolution will be dominated by the gradual dispersal of existing structures as accelerating expansion carries galaxies farther apart. The observational evidence for cosmic acceleration comes from multiple independent measurement techniques that all confirm the same basic picture. Type Ia supernova provide direct distance measurements showing that cosmic expansion has accelerated. Baryon acoustic oscillations in galaxy clustering patterns provide a standard ruler that traces cosmic expansion history. Cosmic microwave background observations constrain cosmic geometry and energy content. Dr. Daniel Eisenstein's analysis of baryon acoustic oscillations in the Sloan Digital Sky Survey reveals sound wave patterns imprinted in the distribution of galaxies that reflect acoustic oscillations in the plasma of the early universe. These patterns provide precise measurements of cosmic expansion at different epochs, confirming the supernova evidence for recent acceleration. The cosmic microwave background observations from the WMAP and Planck satellites provide additional evidence for dark energy through measurements of cosmic geometry. These observations show that the universe is geometrically flat, requiring a total energy density very close to the critical density. When all forms of matter are accounted for, approximately 68% of the critical density must consist of dark energy. Recent gravitational lensing surveys provide independent confirmation of cosmic acceleration through measurements of how dark energy affects the growth of cosmic structure over time. As dark energy becomes more dominant, it suppresses the growth of dark matter clumps and galaxy clusters, creating observable effects in weak lensing statistics. Dr. Sarah Bridle's analysis of weak lensing data from the Dark Energy Survey shows that the growth of cosmic structure has slowed over the past several billion years in precisely the way predicted by dark energy models. These observations provide crucial tests of whether apparent cosmic acceleration results from dark energy or from modifications to Einstein's gravity theory. The future implications of cosmic acceleration are both dramatic and inevitable. If dark energy maintains constant density as space expands, cosmic acceleration will continue indefinitely, eventually carrying every galaxy outside our local group beyond our observable horizon. Dr. Lawrence Krauss's calculations of cosmic evolution predict that accelerating expansion will make the universe increasingly cold, dark, and empty over time. Within approximately 100 billion years, all galaxies outside our local group will have receded so far that their light can no longer reach us, making them effectively disappear from the observable universe. This cosmic isolation will fundamentally alter the night sky as viewed from Earth or any planet in the Milky Way. Future astronomers will see only the merged remnant of the Milky Way and Andromeda galaxies surrounded by empty darkness, with no evidence for the existence of the billions of other galaxies that populate today's universe. The ultimate fate of an accelerating universe depends on the specific properties of dark energy. If dark energy maintains exactly constant density, corresponding to Einstein's cosmological constant. Cosmic acceleration will continue forever, leading eventually to the Big Rip scenario, where accelerating expansion becomes so extreme that it overcomes all gravitational forces and tears apart galaxies, stars, planets, and eventually atoms themselves. Alternative dark energy models predict different cosmic futures. Quintessence models, where dark energy slowly evolves over time, might lead to scenarios where dark energy eventually decays or changes sign, potentially causing cosmic expansion to reverse into a Big Crunch collapse phase. Dr. Robert Caldwell's research on phantom dark energy explores scenarios where dark energy density increases over time, leading to super-accelerated expansion that could tear apart all gravitationally bound structures within a finite time. In the most extreme phantom models, the Big Rip could occur within 20 to 30 billion years. Recent observations attempt to distinguish between these different dark energy models through precision measurements of the dark energy equation of state parameter, W, and its evolution over time. Current data favor a cosmological constant, W equals -1, but uncertainties still allow for slowly evolving quintessence models. The Dark Energy Spectroscopic Instrument, DESI, and the Euclid Space Mission represent next-generation observational programs designed to measure dark energy properties with unprecedented precision. These surveys will map the three-dimensional distribution of millions of galaxies and quasars to trace cosmic expansion history and structure growth with percent-level accuracy. Dr. Ofer Lahav's research on dark energy surveys shows that these future observations could distinguish between cosmological constant and evolving dark energy models, potentially revealing whether dark energy represents a fundamental property of spacetime or a dynamic field that changes over cosmic time. The philosophical implications of cosmic acceleration extend beyond astrophysics to fundamental questions about the nature of space, time, and energy. If dark energy represents the energy of empty space itself, then the vacuum contains vastly more energy than any other component of reality, making nothingness the most energetically significant aspect of existence. This possibility challenges our intuitive understanding of emptiness and fullness. Rather than being the absence of energy, empty space might be the most energy-rich environment in the universe, containing quantum fields and vacuum fluctuations that determine cosmic evolution on the largest possible scales. Recent research in quantum field theory attempts to understand why vacuum energy appears to have precisely the right value to drive observed cosmic acceleration while avoiding the enormous vacuum energy densities predicted by naive quantum field calculations. This cosmological constant problem represents one of the most profound puzzles in theoretical physics. The acceleration of cosmic expansion also raises questions about the relationship between local and global physics. While cosmic expansion accelerates on the largest scales, locally bound systems like galaxies, stars, and planets remain unaffected by dark energy because gravitational and electromagnetic forces easily overcome dark energy effects on these smaller scales. This scale separation suggests that the universe operates according to different physical principles at different scales, with dark energy dominating cosmic dynamics, while having negligible effects on the formation and evolution of complex structures capable of supporting life and consciousness. As we prepare to explore how much mass remains missing from our cosmic senses, remember that the cosmic acceleration surrounding you represents the dominant physical process in the current universe, a runaway expansion that will ultimately carry every distant galaxy beyond the reach of observation, leaving future civilizations in a cosmos that appears far emptier and more mysterious than the rich, galaxy-filled universe we observe today. Chapter 6. Missing Mass. When astronomers attempt to weigh the universe by counting every star, every galaxy, every gas cloud, and every form of matter they can observe across the entire cosmos, They discover a cosmic accounting problem so severe that it suggests our understanding of reality is fundamentally incomplete. The total mass of everything visible represents only about 15% of the gravitating matter needed to explain the motions of galaxies and the large-scale structure of the universe. The remaining 85% consists of completely unknown forms of matter that interact gravitationally, but remain invisible to every detection method we possess. This missing mass problem manifests most dramatically in the rotation curves of spiral galaxies, where stars in the outer regions orbit far too quickly to be held in place by the gravity of the visible matter alone. Dr. Vera Rubin's pioneering observations in the 1970s showed that instead of the declining orbital speeds predicted by Newton's laws when applied to visible matter distributions, galaxy rotation curves remain remarkably flat, extending far beyond the visible edges of galactic disks. The mathematical analysis is straightforward but shocking. If visible matter provided all the gravitational force holding galaxies together, stars in the outer regions should escape into intergalactic space within a few 100 million years. The fact that galaxies maintain stable disk structures over billions of years requires the presence of additional matter with roughly 5 times the mass of all visible stars and gas combined. Recent surveys like the Sloan Digital Sky Survey have confirmed that this missing mass problem extends beyond individual galaxies to galaxy clusters, groups, and the large-scale structure of the cosmic web. Every gravitationally bound system in the universe, from the smallest dwarf galaxies to the largest galaxy superclusters, contains far more gravitating matter than can be accounted for by visible components. Dr. Stacy McGaw's analysis of galaxy rotation curve data spanning 4 decades of observations shows that the missing mass problem is universal across galaxy types, masses, and environments. Low surface brightness galaxies, high surface brightness galaxies, elliptical galaxies, irregular galaxies, and galaxy clusters all require similar amounts of additional matter to explain their gravitational dynamics. The cosmic microwave background radiation provides independent evidence for missing mass through precise measurements of the acoustic oscillations that shaped matter distribution in the early universe. These oscillations depended on the total amount of matter that could participate in gravitational clustering, including both visible matter and any additional gravitating matter that remained invisible to electromagnetic radiation. Dr. Wayne Hu's analysis of cosmic microwave background data from the Planck satellite shows that the total matter density required to explain these acoustic patterns is approximately 5.5 times larger than the density of visible matter. This cosmic microwave background evidence for missing mass is completely independent of galaxy rotation curves and galaxy cluster dynamics, yet it points to exactly the same conclusion. Big Bang nucleosynthesis calculations provide additional constraints on the missing mass problem by determining how much ordinary matter, protons and neutrons, could have been produced in the early universe. Dr. Gary Steigman's research shows that the observed abundances of light elements like deuterium, helium, and lithium are consistent with ordinary matter, comprising only about 4.9% of the universe's total energy content. Since observations require matter to comprise about 31% of cosmic energy content to explain structure formation and cosmic microwave background patterns, the vast majority of gravitating matter must consist of non-ordinary matter that doesn't participate in electromagnetic interactions or Big Bang nucleosynthesis processes. This non-ordinary matter component, called dark matter, must have been present in the early universe in sufficient quantities to provide the gravitational seeds around which ordinary matter could later condense to form stars and galaxies. Without dark matter's gravitational scaffolding, the universe would have remained a smooth, expanding gas cloud incapable of developing the complex structures necessary for star formation and planetary systems. Computer simulations of cosmic structure formation, such as the Millennium Simulation and the Illustris Project, demonstrate that dark matter is essential for reproducing the observed patterns of galaxy clustering and cosmic web structure. These simulations show that ordinary matter follows dark matter's gravitational influence, flowing along dark matter filaments to accumulate at nodes where galaxy formation can occur. Dr. Mark Vogelsberger's research using the illustrious simulation shows remarkable agreement between theoretical predictions and observational data when dark matter comprises approximately 85% of all gravitating matter. The same simulations produce completely unrealistic cosmic structure when dark matter is removed or significantly reduced in abundance. Recent gravitational lensing observations provide perhaps the most direct evidence for dark matter as a distinct substance rather than a modification of gravitational laws. When galaxy clusters collide, the dark matter components pass through each other essentially unimpeded because dark matter interacts only gravitationally, while the ordinary matter components experience friction and electromagnetic interactions. Dr. Marusa Braddock's analysis of the bullet cluster collision shows clear spatial separation between the locations of ordinary matter, traced by X-ray emission from hot gas, and gravitational mass, traced by weak lensing of background galaxies. This separation can only be explained if most gravitational mass consists of collisionless dark matter particles rather than ordinary matter or modified gravity effects. The search for dark matter particles represents one of the most intensive experimental programs in modern physics, with underground detectors attempting direct detection, particle accelerators searching for dark matter production, and space-based telescopes looking for signals from dark matter annihilation or decay processes. Dr. Elena Opperl's xenon collaboration operates increasingly sensitive liquid xenon detectors designed to catch the rare occasions when dark matter particles might scatter off atomic nuclei. Despite decades of searching with steadily improving sensitivity, no confirmed dark matter detection has been achieved, placing stringent limits on how dark matter particles might interact with ordinary matter through non-gravitational forces. The Large Hadron Collider at CERN has searched for dark matter particles that might be produced in high-energy proton collisions, but these searches have not yet revealed any evidence for stable weakly interacting particles with the properties required to account for cosmic dark matter. These null results suggest that dark matter particles, if they exist, have interaction strengths and masses very different from theoretical expectations. Recent theoretical research explores alternative dark matter candidates beyond the standard weakly interacting massive particles WIMPs that have guided most experimental searches. Axions, sterile neutrinos, primordial black holes, and more exotic possibilities like dark photons or hidden sector particles provide alternative explanations for the missing mass problem. Dr. Lisa Randall's research on dark matter models suggests that dark matter might exist in its own dark sector with its own forces and interactions that remain completely hidden from ordinary matter, except through gravitational effects. This dark sector might contain complex physics, including dark atoms, dark chemistry, and even dark stars composed entirely of dark matter. Modified gravity theories provide an alternative approach to the missing mass problem by proposing that gravitational laws differ from Einstein's general relativity on galactic and cosmic scales. Modified Newtonian dynamics, MOND, and other alternative gravity theories can explain galaxy rotation curves without invoking dark matter, but they struggle to account for cosmic microwave background observations and gravitational lensing effects. Dr. Stacy McGough's research on MOND shows that this alternative gravity theory provides excellent fits to galaxy rotation curve data across a wide range of galaxy types and masses. However, MOND requires additional assumptions about the cosmic microwave background and structure formation that make it less elegant than dark matter models for explaining the full range of cosmological observations. Recent observations from gravitational wave detectors provide new opportunities to search for dark matter through precision measurements of how gravitational waves propagate through regions of space contain dark matter concentrations. If dark matter particles have any interactions beyond gravity, they might create detectable effects on gravitational wave signals from distant sources. The missing mass problem extends beyond dark matter to include uncertainties in how much ordinary matter exists in forms that are difficult to observe directly. Intergalactic gas clouds, brown dwarf stars, free-floating planets, and black holes might account for some fraction of the apparent missing mass, though current estimates suggest these components cannot resolve the entire missing mass problem. Dr. Julianne Dalcanton's research on stellar mass functions and galaxy formation efficiency suggests that significant amounts of ordinary matter might exist in very low-mass stars, failed stars, and other dim objects that contribute to galactic gravitational fields while remaining below current detection thresholds. However, Big Bang nucleosynthesis constraints limit how much additional ordinary matter could exist without violating observed light element abundances. The implications of the missing mass problem extend far beyond astronomy to fundamental questions about the nature of matter and gravity in the universe. If 85% of gravitating matter consists of unknown substances, then our understanding of matter is based on studying a small, potentially unrepresentative sample of cosmic material. This possibility suggests that the standard model of particle physics, which successfully describes all known particles and forces, might represent only a tiny fraction of the fundamental physics operating in the universe. Dark matter particles, if they exist, would require extensions to the standard model that could revolutionize our understanding of fundamental forces and particle interactions. Recent research in particle physics explores theoretical frameworks like supersymmetry, extra dimensions, and string theory that predict new particles and forces beyond the standard model. These theories often include natural dark matter candidates, providing connections between particle physics experiments and cosmological observations of missing mass. As we prepare to explore the technological and theoretical limits that constrain our ability to detect the universe's hidden components, remember that the missing mass surrounding and permeating every cosmic structure represents one of the most profound mysteries in science. Evidence that reality contains vast realms of matter and energy that remain completely hidden from direct observation, despite determining the structure and evolution of everything we can see. Chapter 7. Detection Limits. The technological and theoretical barriers preventing us from directly detecting the hidden 96% of the universe reveal fundamental limitations that extend far beyond current scientific instruments to challenge our most basic assumptions about what it means for something to be observable. These detection limits aren't simply engineering problems waiting to be solved. They represent encounters with the deepest constraints imposed by the laws of physics themselves, suggesting that some aspects of reality might be forever beyond the reach of direct measurement by beings composed of ordinary matter. The electromagnetic spectrum encompasses all forms of light and radiation that our telescopes can detect, from radio waves with wavelengths of kilometers down to gamma rays with wavelengths smaller than atomic nuclei. Every astronomical observation throughout history has relied on detecting electromagnetic radiation emitted, absorbed, or scattered by cosmic objects, creating a comprehensive picture of the universe's visible components. However, dark matter and dark energy interact so weakly with electromagnetic radiation that they remain essentially invisible across the entire electromagnetic spectrum. Dark matter particles don't emit light, don't absorb light, and don't scatter light in any detectable way, making them completely transparent to all forms of electromagnetic radiation from radio to gamma ray wavelengths. Dr. Catherine Freese's research on dark matter detection shows that this electromagnetic invisibility isn't a temporary limitation awaiting better telescopes, but rather a fundamental property that makes dark matter undetectable through any electromagnetic means, regardless of technological advancement. Dark matter exists in a physics regime where electromagnetic interactions are either completely absent or suppressed by factors of 1040 or more compared to gravitational interactions. The detection limits for dark energy are even more severe because dark energy appears to be a property of space itself rather than a collection of particles that could potentially be observed directly. Dark energy manifests only through its effects on cosmic expansion and structure formation, making it detectable solely through precise measurements of cosmic geometry and dynamics over vast distances and timescales. Recent attempts to detect dark matter through direct interaction with ordinary matter have pushed experimental sensitivity to unprecedented levels. Underground laboratories like the Large Underground Xenon Lux experiment and the Xenon collaboration operate detectors containing hundreds of kilograms of liquid xenon shielded from cosmic radiation by kilometers of rock. Dr. Elena Opral's analysis of xenon data shows that these experiments can detect individual nuclear recoils with energies as low as a few keV, sensitive enough to catch dark matter particles if they interact with ordinary nuclei at rates predicted by many theoretical models. However, after years of operation with steadily improving sensitivity, no confirmed dark matter signals have been detected. The null results from direct detection experiments don't prove that dark matter doesn't exist, but they do constrain how strongly dark matter particles can interact with ordinary matter through non-gravitational forces. Current limits rule out interaction cross-sections larger than about y-45 square centimeters, roughly 10 trillion times smaller than typical nuclear interaction cross-sections. These constraints push dark matter into a regime where particles might pass through the entire Earth without interacting even once with ordinary matter. Dr. Gianfranco Bertoni's research on dark matter physics shows that such weakly interacting particles would be essentially undetectable through any conceivable direct detection method, regardless of detector size or sensitivity improvements. Particle accelerators like the Large Hadron Collider at CERN provide another approach to dark matter detection by attempting to create dark matter particles through high-energy collisions between ordinary matter particles. These experiments search for evidence of invisible particles that carry away energy and momentum from collision events without leaving traces in detector systems. Dr. Sarah Malik's analysis of LHC data shows that these experiments have ruled out many theoretical dark matter candidates in specific mass and interaction strength ranges. However, the parameter space for possible dark matter particles is enormous, and accelerator experiments can only probe a small fraction of theoretically viable dark matter models. The detection limits for dark matter become even more severe when considering that dark matter might exist in its own dark sector with its own forces and interactions that are completely decoupled from ordinary matter physics except through gravity. Dr. Lisa Randall's research on hidden sector dark matter explores scenarios where dark matter particles interact only with each other and with gravity, making them forever undetectable through any electromagnetic or nuclear interaction. Gravitational wave detectors like LIGO and Virgo represent a fundamentally new observational window that might provide indirect methods for studying dark matter through its gravitational effects on spacetime itself. Recent research explores whether dark matter clumps or dark matter particle interactions might create detectable gravitational wave signatures. Dr. Vup Mandik's research on gravitational wave astronomy suggests that future space-based detectors, like the Laser Interferometer Space Antenna, LISA, might be sensitive to gravitational waves produced by dark matter interactions or the motion of dark matter structures through space. However, these signals would likely be extremely weak and difficult to distinguish from astrophysical sources. The cosmic microwave background radiation provides the most precise measurements of dark matter properties through its effects on acoustic oscillations in the early universe plasma. The Planck satellite has measured these temperature fluctuations with extraordinary precision, constraining dark matter's interaction strength particle mass, and abundance to percent-level accuracy. Dr. Anthony Lewis's analysis of cosmic microwave background data shows that future improvements in measurement precision are unlikely to reveal additional information about dark matter properties beyond what is already known. The cosmic microwave background essentially provides a complete census of dark matter's gravitational effects in the early universe, but it cannot reveal the particle physics nature of dark matter itself. Weak gravitational lensing observations represent perhaps the most direct method for mapping dark matter distribution throughout the universe. When light from distant galaxies passes through regions containing dark matter, the gravitational effects subtly distort background galaxy shapes in ways that reveal dark matter's three-dimensional structure. Dr. Catherine Haymans' research, using weak lensing data from surveys like the Kilo-Degree Survey and the Dark Energy Survey, has created detailed maps of dark matter distribution covering billions of light years. However, these observations can only detect dark matter's gravitational effects and provide no information about the fundamental nature of dark matter particles. The detection limits for dark energy are constrained by cosmic variance, the fundamental limitation that we can observe only one universe and cannot repeat cosmic evolution experiments with different initial conditions. Dr. Max Tegmark's research on cosmic variance shows that no future observations can improve dark energy measurements beyond limits imposed by having access to only a single cosmic sample. Recent theoretical research explores whether dark matter and dark energy might be detectable through their effects on fundamental constants or through violations of equivalence principle predictions. Dr. Tessa Baker's work on testing general relativity suggests that precision measurements of gravitational effects might reveal subtle signatures of dark sector physics. However, these tests require measurement precisions that approach or exceed the theoretical limits imposed by quantum mechanics and the discrete nature of matter and energy. The uncertainty principle and shot noise from finite particle numbers create fundamental barriers to arbitrarily precise measurements of gravitational and cosmological parameters. Astronomical observations are also limited by cosmic evolution and the finite age of the universe. Many dark matter and dark energy effects become apparent only over cosmological timescales of billions of years, making it impossible to observe multiple cycles of cosmic evolution or to study the long-term behavior of dark components. Dr. Sean Carroll's research on the arrow of time suggests that some aspects of dark energy physics might be fundamentally unobservable because they depend on the global structure of space-time rather than local physical processes that can be measured within human lifetimes or even within the age of civilizations. The technological limits of detection are approaching fundamental physical barriers imposed by quantum mechanics, thermodynamics, and the structure of space-time itself. Future improvements in detector sensitivity must overcome quantum noise, thermal fluctuations, and gravitational wave interference from sources throughout the universe. Dr. Kip Thorne's research on gravitational wave detection shows that the most sensitive conceivable detectors would be limited by quantum uncertainty in the positions of test masses and by gravitational wave backgrounds from astrophysical sources throughout the cosmos. These limits represent absolute barriers beyond which no classical measurement system can operate. Recent research in quantum information theory explores whether quantum sensors might overcome some classical detection limits through quantum entanglement and squeeze states that reduce measurement uncertainty below classical limits. However, these quantum advantages come at the cost of increased complexity and vulnerability to environmental decoherence. Perhaps most fundamentally, the detection limits we encounter might reflect limitations in how consciousness and ordinary matter can interact with the broader universe. If consciousness depends on electromagnetic interactions between ordinary matter particles, then conscious beings might be forever limited to perceiving only the small fraction of reality that participates in electromagnetic processes. Dr. David Chalmers' research on consciousness and physics suggests that the hard problem of consciousness might extend to cosmology. Consciousness might be inherently limited to observing and understanding only those aspects of reality that can interact with the electromagnetic processes that make conscious observation possible. As we prepare to explore how parallel dimensions and extra-dimensional physics might explain the hidden universe, remember that the detection limits surrounding dark matter and dark energy might represent more than technological challenges. They might be fundamental features of reality that ensure most of the universe remains forever hidden from direct observation by conscious beings like ourselves. Chapter 8. Parallel Dimensions. Beyond the familiar 3 dimensions of space and 1 dimension of time that define our everyday experience lies a hidden architecture of reality so vast and complex that it might explain why 96% of the universe remains invisible to us, a system of parallel dimensions and extra-dimensional spaces where the missing matter and energy of our cosmos might exist in forms completely inaccessible to beings confined to our limited dimensional slice of a much larger reality. The mathematical framework for extra dimensions emerges from string theory, which requires a minimum of 10 or 11 total dimensions to provide a consistent quantum description of all fundamental forces and particles. Dr. Edward Witten's research on M-theory suggests that our familiar 4-dimensional spacetime represents just a tiny slice of an 11-dimensional reality, with the additional 7 dimensions either compacted to microscopic sizes or extending into parallel spaces that don't intersect our dimensional domain. These extra dimensions aren't just abstract mathematical constructs, but could provide physical locations where dark matter and dark energy exist in forms that are fundamentally invisible to us because they operate in dimensional directions we cannot access or perceive. From our 3-dimensional perspective, matter and energy in parallel dimensions would appear to be missing even though they exist in abundance, just micrometers away in directions we cannot point to or move through. Dr. Elisa Randall's research on warped extra dimensions demonstrates how gravity can propagate through all dimensions of space while other forces remain confined to our familiar 3-dimensional brain. If dark matter consists of particles that exist primarily in extra dimensions, they would interact with us only through gravitational effects while remaining completely invisible to electromagnetic radiation confined to our dimensional space. The concept of brand-new cosmology, developed by Dr. Nima Akni-Hamd and collaborators, proposes that our entire observable universe exists on a 3-dimensional membrane floating in higher dimensional space. Other branes could exist parallel to ours, potentially containing entire universes of matter and energy that remain completely hidden because they don't share our dimensional space. These parallel universes could be located just millimeters away from us in extra-dimensional directions, containing their own stars, galaxies, and possibly even life forms that remain forever invisible because light and matter cannot travel between branes. The gravitational effects of these parallel universes would be the only way we could detect their existence, potentially explaining the apparent dark matter and dark energy that dominate our cosmic observations. Recent theoretical research explores whether the cosmic acceleration attributed to dark energy might result from gravitational interactions between our brain and parallel branes in extra-dimensional space. Dr. Gia Vali's work on DGP, Vali Gabadadzi Parati, brand-new models shows how modifications to gravity in extra dimensions could create apparent cosmic acceleration without requiring any dark energy component within our 4-dimensional spacetime. If cosmic acceleration results from extra-dimensional gravitational effects, then the mysterious dark energy that comprises 68% of our universe's energy content might actually be ordinary matter and energy existing in parallel dimensions. The acceleration we observe would be a geometric effect of how our brain moves through higher dimensional space rather than evidence for exotic energy fields within our dimensional domain. The hierarchy problem in particle physics provides additional motivation for extra-dimensional explanations of missing matter and energy. The enormous difference between the strength of gravity and other fundamental forces might be explained if gravity is diluted by spreading through extra dimensions, while electromagnetic and nuclear forces remain confined to our three-dimensional space. Dr. Salvas Dimopoulos' research on large extra dimensions suggests that if gravity propagates through extra dimensions of millimeter size, then the fundamental strength of gravity would be comparable to other forces at microscopic scales. The apparent weakness of gravity in our three-dimensional experience would result from gravitational force spreading through extra-dimensional volumes much larger than ordinary particles can access. These large extra dimensions could provide enormous amounts of space where dark matter particles might exist in forms that interact gravitationally with our three-dimensional space while remaining completely hidden from electromagnetic detection. The missing mass problem could be solved if most gravitating matter exists in extra-dimensional regions that are physically real but observationally inaccessible. Experimental tests of extra-dimensional theories focus on searching for deviations from Newton's inverse square law of gravitation at short distances. If gravity propagates through extra dimensions, then gravitational attraction should become stronger than predicted at distances comparable to the size of extra dimensions. Dr. Eric Adelberger's precision tests of gravitational attraction between laboratory masses have confirmed Newton's inverse square law down to distances of approximately 50 micrometers, ruling out extra dimensions larger than this scale. However, smaller extra dimensions or more complex extra-dimensional geometries remain viable possibilities for explaining cosmic dark components. The cosmic microwave background radiation provides constraints on extra-dimensional models through precision measurements of cosmic expansion and structure formation history. Extra dimensions would affect cosmic dynamics in ways that should be detectable through careful analysis of temperature fluctuations in the cosmic microwave background. Dr. Mark Troughton's analysis of cosmic microwave background data shows that certain extra-dimensional models can be consistent with observations if the extra dimensions have specific sizes and geometries. However, these constraints significantly limit the parameter space available for extra-dimensional explanations of dark matter and dark energy. Recent research in holographic duality suggests a fundamentally different perspective on extra dimensions and hidden reality. The NDC correspondence, discovered by Dr. Juan Maldacena, demonstrates that certain types of higher dimensional gravity theories are mathematically equivalent to lower dimensional quantum field theories operating on boundary surfaces. If our three-dimensional reality emerges from information processing on two-dimensional surfaces, then the missing 96% of the universe might exist as additional information encoded on these boundary surfaces but not accessible to three-dimensional observers. The dark components would be literally hidden within the mathematical structure that generates our perceived three-dimensional spacetime. Compactified extra dimensions provide another framework for understanding how parallel dimensions might contain hidden reality. If extra dimensions are curved into tiny geometric shapes called Calabi-Yau manifolds, then particles and energy can be trapped in different regions of these compact spaces while remaining invisible from our dimensional perspective. Dr. Brian Greene's research on string compactification shows that different regions of compact extra dimensions can support different types of physics, potentially creating hidden sectors of reality that operate according to completely different force laws and particle interactions. These hidden sectors could contain the dark matter and dark energy that dominate cosmic evolution while remaining undetectable through ordinary matter interactions. Quantum field theory in extra dimensions reveals additional possibilities for hidden reality through mechanisms called dimensional transmutation and spontaneous compactification. These processes can create situations where extra dimensions change size over cosmic time, or where matter and energy can transition between different dimensional configurations. Dr. Joseph Polchinski's research on D-branes in string theory shows how matter can be confined to different dimensional surfaces within the same extra-dimensional space. Dark matter might exist on parallel branes that don't directly intersect our brain, making it gravitationally influential but electromagnetically invisible. Recent cosmological observations provide indirect tests of extra-dimensional theories through measurements of cosmic expansion, structure formation, and gravitational wave propagation. If extra dimensions affect cosmic dynamics, these effects should be detectable through precision cosmological measurements, even if extra dimensions cannot be probed directly. Dr. Claudia de Ram's research on massive gravity and extra-dimensional modifications to general relativity explores how additional dimensions might affect gravitational wave propagation and cosmic expansion in ways that could be detected by current and future observational programs. The philosophical implications of parallel dimensions challenge our most basic assumptions about the nature of space, reality, and existence itself. If most of the universe exists in dimensions we cannot access, then our entire scientific understanding of reality is based on studying a tiny, potentially unrepresentative slice of a much larger and more complex cosmos. This dimensional limitation might explain not just the missing matter and energy in our universe, but also fundamental puzzles about consciousness, the fine-tuning of physical constants, and the apparent rarity of complex life. Parallel dimensions could contain vastly more reality than our accessible universe, potentially including countless other forms of life and consciousness that remain forever hidden from our perception. Recent research in quantum gravity suggests that the boundary between accessible and hidden dimensions might not be absolute. Quantum fluctuations and gravitational effects might create temporary connections or wormholes between parallel dimensional spaces, potentially allowing limited information exchange between normally separated realities. Dr. Leonard Susskind's research on wormhole physics and quantum entanglement explores whether quantum correlations might extend across dimensional boundaries, creating hidden connections between our universe and parallel dimensional spaces. These quantum connections might influence cosmic evolution in ways that appear as dark matter and dark energy effects from our limited dimensional perspective. As we prepare to explore multiverse theories and their implications for hidden reality, remember that the space immediately around you might be permeated by entire universes of matter, energy, and possibly consciousness that exist in parallel dimensions, just micrometers away in directions you cannot perceive, interact with, or even imagine from your confined perspective within the narrow dimensional slice you call reality. Chapter 9. Multiverse Reality. Beyond the boundaries of our observable universe, stretching through dimensions of possibility that dwarf our cosmic horizon by incomprehensible factors, lies a multiverse so vast that our entire observable reality, containing hundreds of billions of galaxies across 93 billion light-years, represents less than a single atom in an infinite ocean of parallel universes, each containing its own versions of space, time, matter, and energy that collectively might explain why our particular cosmic domain appears to be missing 96% of its expected content. The mathematical foundation for multiverse theory emerges from cosmic inflation, the process that drove exponential expansion during the first fraction of a second after the Big Bang. Dr. Andre Lind's research on chaotic inflation demonstrates that once inflation begins in any region of space, it naturally creates infinite patches of inflated spacetime, each of which can develop into a separate universe with its own physical laws and constants. These parallel universes aren't just theoretical possibilities, but appear to be inevitable consequences of the same inflationary physics that explains the observed flatness, homogeneity, and structure of our own universe. If inflation theory correctly describes our cosmic origins, then our observable universe represents just one bubble in an infinite sea of inflating spacetime where every possible variation of physical laws and cosmic evolution plays out across countless parallel realities. Dr. Max Tegmark's classification of multiverse levels provides a framework for understanding different types of parallel realities. Level I multiverses contain regions beyond our observable horizon where the same physics operates, but initial conditions differ. Level 2 multiverses contain regions where fundamental constants and physical laws take different values. Level 3 multiverses contain quantum mechanical branches where different measurement outcomes occur. Level 4 multiverses contain all possible mathematical structures as physically real universes. The implications for our cosmic mass shortage become profound when viewed from a multiverse perspective. If our universe represents one bubble in an infinite multiverse, then the matter and energy we observe might represent only the portion that happens to exist within our particular cosmic domain, while vast amounts of additional reality exist in parallel universes that share the same underlying spacetime but remain causally disconnected from our observations. Recent research in string theory suggests that different regions of the multiverse might have different numbers of large spatial dimensions, different particle physics, and even different mathematical relationships between space and time. Dr. Leonard Susskind's work on the string theory landscape predicts approximately 10,500 different possible vacuum states, each corresponding to a different universe with its own physics and cosmological parameters. In this vast landscape of possibilities, universes with our particular values of dark matter and dark energy densities would be extremely rare, occurring perhaps once in every 10,120 cosmic domains. The fact that we observe precisely the combination of visible matter, dark matter, and dark energy that allows complex structure formation might not reflect fundamental physics, but rather selection effects. We exist in this particular cosmic domain precisely because it permits the development of observers. The anthropic principle provides a framework for understanding this selection effect through what Dr. Brandon Carter calls observer selection bias. In an infinite multiverse containing every possible combination of physical parameters, conscious observers will necessarily find themselves in universes where the physical constants permit the development of complexity, chemistry, and ultimately, life and consciousness. From this anthropic perspective, the apparent fine-tuning of dark energy density, dark matter abundance, and ordinary matter properties isn't mysterious but inevitable. Universes with different parameter combinations either collapse too quickly, expand too rapidly, or fail to form the complex structures necessary for conscious observers to evolve and contemplate cosmological questions. Eternal inflation theory, developed by Dr. Paul Steinhardt and Dr. Andreas Albrecht, suggests that inflationary expansion continues forever in most regions of the multiverse while occasionally ending in finite patches that become individual universes like ours. This process creates an infinite hierarchy of cosmic domains where every possible physics is realized infinitely many times across the eternal inflation landscape. Recent calculations by Dr. Alex Vilenkin show that eternal inflation produces infinite copies of any finite region of spacetime, including exact duplicates of our observable universe with identical histories, structures, and even conscious observers. In an infinite multiverse, every possible cosmic configuration occurs infinitely often, making our particular universe, with its specific dark matter and dark energy properties, inevitable rather than improbable. The quantum mechanical many-worlds interpretation provides another pathway to multiverse reality through the continuous branching of quantum measurement outcomes. Dr. Hugh Everett III's theory suggests that every quantum measurement splits the universe into parallel branches containing all possible outcomes, creating an infinite tree of parallel realities that share common quantum mechanical origins but diverge through different sequences of measurement results. In the quantum multiverse, dark matter and dark energy might exist in superposition across multiple parallel branches, with our particular branch experiencing only a small fraction of the total quantum reality. The missing 96% might exist in parallel quantum branches that remain causally connected through quantum entanglement while being observationally inaccessible from our specific branch of the quantum state vector. Dr. David Deutsch's research on quantum computation and parallel universes suggests that quantum computers might provide direct evidence for the multiverse by performing calculations that require computational resources exceeding what is available in any single universe. Quantum algorithms like Shor's factoring algorithm appear to harness computational power from parallel quantum branches to solve problems that would be impossible using classical computation. Recent developments in cosmological observations provide potential tests of multiverse theories through their predictions for cosmic parameters and structure formation. If our universe is one bubble in an infinite multiverse, then cosmic parameters like the cosmological constant, dark matter density, and spatial curvature should fall within the ranges that permit observer formation but not be fine-tuned beyond what observer selection requires. Dr. Steven Winberg's anthropic prediction for the cosmological constant represents one of the most successful applications of multiverse reasoning to cosmological observations. By assuming that vacuum energy takes random values across the multiverse, but conscious observers only evolve in universes where vacuum energy permits structure formation, Winberg predicted the observed dark energy density decades before it was measured. The holographic principle provides additional insight into multiverse structure by suggesting that the information content of any spatial region is encoded on its boundary surface. If our universe is holographically encoded on a distant boundary, then parallel universes might be encoded on nearby boundary regions, creating a vast library of cosmic information where every possible universe is stored in adjacent holographic sectors. Dr. Juan Naldacina's ADS-CFT correspondence demonstrates mathematically how this holographic encoding works in specific cases, showing that higher dimensional spacetime can be exactly equivalent to lower dimensional information processing on boundary surfaces. The multiverse might exist as a vast holographic library where every possible cosmic history is simultaneously encoded and accessible through appropriate boundary calculations. Recent research in digital physics and computational cosmology explores whether the multiverse might be fundamentally computational rather than physical. Dr. Stephen Wolfram's investigations of cellular automata show that simple computational rules can generate arbitrarily complex structures that appear to follow physical laws, indistinguishable from our observed universe. If the multiverse operates as a vast computational system exploring all possible algorithmic structures, then our universe represents one computational branch among infinite others. The dark matter and dark energy we observe might be computational artifacts that arise when one computational universe interacts with or receives input from parallel computational processes. The implications of multiverse reality extend beyond cosmology to fundamental questions about the nature of existence, consciousness, and identity. If infinite copies of yourself exist across the multiverse, which one is the real you? Are you all equally real, or do you have a unique identity that distinguishes you from your multiverse duplicates? Dr. Derek Parfit's research on personal identity suggests that the concept of unique selfhood might be an illusion that breaks down in a multiverse context. Your identity might be better understood as a pattern of information processing that is instantiated across multiple parallel realities, with no fundamental difference between your current branch and your multiverse alternatives. Recent research in quantum consciousness explores whether conscious awareness might extend across multiple multiverse. branches through quantum entanglement effects in neural microtubules. Dr. Stuart Hameroff's orchestrated objective reduction theory suggests that consciousness might naturally access information from parallel quantum branches, potentially explaining phenomena like creativity, intuition, and the apparent unreasonable effectiveness of mathematical thinking. The cosmic implications of multiverse reality suggest that the missing mass and energy in our universe might not be missing at all, but rather distributed across parallel cosmic domains that share our space but exist in separate causal regions. From a multiverse perspective, asking, "Where's the missing 96% of the universe?" might be equivalent to asking, "Where are all the books that aren't in this library?" They exist in abundance, just not in our particular cosmic domain. As we prepare to explore the observable boundaries that limit our knowledge of cosmic reality, remember that the universe you inhabit might be just one thread in an infinite tapestry of parallel realities where every possible version of cosmic evolution plays out simultaneously, making your particular cosmic domain, with its specific balance of visible and dark components, inevitable in the vast ensemble of multiverse possibilities. Chapter 10. Observable boundaries. At approximately 46.5 billion light-years from Earth in every direction lies an absolute boundary beyond which no information can ever reach us, the edge of our observable universe, where the expansion of space itself creates an impenetrable barrier that forever limits our knowledge of cosmic reality and ensures that most of the universe will remain permanently hidden from any observation, measurement, or scientific investigation conducted by beings trapped within our cosmic horizon. This observable boundary isn't just a temporary limitation awaiting better telescopes or advanced technology. It represents a fundamental constraint imposed by the finite age of the universe and the finite speed of light. Only 13.8 billion years have passed since the Big Bang, meaning that light has had time to travel at most 13.8 billion light-years from distant sources. However, cosmic expansion during this time has carried the sources of this light much farther away, creating the current boundary at 46.5 billion light-years. Dr. Edward Harrison's research on cosmic horizons demonstrates that this observable boundary creates an absolute limit on the amount of information we can ever gather about the universe. Everything beyond the observable horizon exists in a realm of permanent ignorance from our perspective, regardless of how long we wait or how advanced our detection methods become. The mathematics describing these cosmic horizons come from general relativity and the Friedmann equations that govern cosmic expansion. As space expands, distant objects move away from us at speeds that can exceed the speed of light, not through their motion in space, but through the expansion of space itself, carrying them beyond the reach of light signals trying to travel from their locations to ours. Recent observations from the Planck satellite have precisely measured the cosmic microwave background radiation, the most distant light we can observe, emitted when the universe was only 380,000 years old and small enough that this radiation could reach us from all directions. This cosmic microwave background represents the ultimate boundary of electromagnetic observation. We cannot see beyond this to earlier cosmic epochs because the universe was opaque to light during its first 380,000 years. Dr. Max Tegmark's analysis of observational constraints shows that the cosmic microwave background provides our most complete view of cosmic conditions in the early universe. However, this complete view covers only a tiny fraction of the total volume of space that must exist beyond our observable boundaries. If the universe is infinite, as suggested by inflation theory and measurements of cosmic geometry, then our observable universe represents 0% of total cosmic reality. Everything we can see, measure, or study, all the galaxies, all the cosmic structures, all the evidence for dark matter and dark energy might be an infinitesimally small and potentially unrepresentative sample of a much larger cosmos. The cosmic event horizon provides an even more restrictive boundary for future observations. Due to accelerating cosmic expansion driven by dark energy, distant galaxies are receding from us at ever-increasing rates. Galaxies beyond approximately 16 billion light-years distance are already receding so fast that light signals they emit today will never reach us, even if we wait forever. Dr. Lawrence Krauss's calculations of cosmic evolution show that this event horizon is shrinking over time as cosmic acceleration increases. Galaxies that are currently observable will disappear beyond the event horizon within the next 100 billion years as cosmic expansion carries them beyond the reach of any possible future communication or observation. This creates a cosmic isolation effect where future civilizations will live in an increasingly empty universe. Astronomers in the distant future will see only the merged remnant of our local group of galaxies surrounded by empty darkness, with no evidence that billions of other galaxies once populated the cosmos. The particle horizon represents another fundamental boundary that limits our knowledge of cosmic reality. This horizon marks the distance to the farthest regions from which particles or information could have traveled to reach us since the beginning of time. Due to cosmic inflation, this particle horizon is much smaller than the regions of space that must have existed in the early universe. Dr. Alan Guth's research on cosmic inflation shows that inflation stretched quantum fluctuations from microscopic to cosmic scales, but it also created vast regions of space that remain causally disconnected from our observable domain. These disconnected regions could have completely different physical properties, cosmic histories, and matter-energy compositions, while remaining forever hidden beyond our particle horizon. Recent research on cosmic topology explores whether space might be finite but unbounded, like the surface of a sphere, but in 3 dimensions. Dr. Jean-Pierre Luminet's analysis of cosmic microwave background patterns searches for evidence that space wraps around on itself, creating a cosmic hall of mirrors where we might see multiple images of the same cosmic structures from different directions. However, current observations show no evidence for cosmic topology on scales smaller than the observable horizon, suggesting that if space is finite, it's much larger than the regions we can currently observe. This leaves open the possibility that vast amounts of cosmic reality exist beyond our current observational reach but within a finite total volume. The anthropic boundaries provide another layer of observational limits by constraining which aspects of cosmic reality can be directly observed by conscious beings like ourselves. If consciousness depends on complex chemistry and stable environments, then conscious observers can only exist in cosmic regions where physical parameters permit the formation of stars, planets, and biochemical complexity. Dr. Brandon Carter's anthropic reasoning suggests that we necessarily observe cosmic parameters that permit our existence. But this observation bias might prevent us from learning about cosmic regions where different physical laws or conditions prevail. The observable universe might be a tiny island of life-friendly conditions in a vast ocean of cosmic reality that remains uninhabitable and therefore unobservable by beings like us. Technological boundaries impose additional limits on cosmic observations through the finite sensitivity of detection instruments and the quantum mechanical constraints that limit measurement precision. Dr. Kip Thorne's research on gravitational wave detection shows that even the most sophisticated conceivable instruments face fundamental barriers imposed by quantum noise, thermal fluctuations, and gravitational wave backgrounds from astrophysical sources throughout the universe. Recent advances in quantum sensing and squeeze light techniques can overcome some classical measurement limits. But these quantum advantages come at the cost of increased complexity and vulnerability to environmental decoherence. The ultimate limits on astronomical observations might be set by the quantum mechanical properties of matter and energy rather than by engineering constraints. The information theoretic boundaries represent perhaps the most Fundamental limits on cosmic observations. Dr. Seth Lloyd's research on the computational capacity of the universe shows that the total amount of information that can be processed or stored in any finite region of space is limited by thermodynamic and quantum mechanical constraints. If consciousness requires information processing, then conscious observers face absolute limits on how much information they can gather, store, or analyze about cosmic reality. These limits might prevent complete understanding of the universe, even if all cosmic information were theoretically accessible. Recent research in holographic cosmology suggests that these information limits might be even more restrictive than previously thought. If the information content of any spatial volume is limited by the area of its boundary surface rather than its volume, then three-dimensional conscious beings might face severe restrictions on how much cosmic information they can access through any possible observation method. The cosmic variance problem creates statistical boundaries that limit cosmological conclusions even within our observable universe. Because we can observe only one universe with one set of initial conditions, we cannot distinguish between features that represent fundamental physical laws and features that result from the particular cosmic history we happen to inhabit. Dr. Max Tegmark's analysis of cosmic variance shows that some cosmological parameters can never be measured with precision better than approximately 1% regardless of observational improvements, because we lack the ability to observe multiple independent cosmic samples for statistical comparison. The boundary between dark and visible components of the universe might represent a fundamental observational limit that reflects the nature of consciousness itself. If conscious observation depends on electromagnetic interactions between ordinary matter particles, then conscious beings might be inherently limited to observing only those aspects of reality that can participate in electromagnetic processes. Dr. David Chalmers' research on the hard problem of consciousness suggests that this observational limitation might be more than just technological. It might reflect deep connections between consciousness and the physical properties that make matter visible. Conscious beings composed of ordinary matter might be fundamentally incapable of directly observing dark matter and dark energy, regardless of technological advancement. Recent research in quantum cosmology explores whether these observational boundaries might be permeable under special circumstances. Quantum fluctuations and gravitational effects might create temporary windows or wormhole connections that allow limited information transfer between normally disconnected cosmic regions. However, these quantum connections would likely be extremely rare and difficult to detect, providing at best fragmentary glimpses of cosmic reality beyond our normal observational boundaries. The vast majority of the universe would remain forever hidden behind impenetrable cosmic horizons. As we prepare to explore the ultimate truth about humanity's place in the cosmic hierarchy of reality, remember that the observable boundaries surrounding you create a cosmic sphere of knowledge beyond which lies an infinite unknown cosmic realms that might contain more matter, energy, structure, and possibly consciousness than exists within the entire observable universe, yet remain forever beyond the reach of human observation and understanding. Chapter 11. Ultimate Truth. As we reach the profound conclusion of our journey into the hidden cosmos, we arrive at a truth so fundamental that it redefines not just our understanding of the universe, but our comprehension of what it means to exist as conscious beings in a reality where everything we can observe, measure, or interact with represents less than 4% of what actually exists around us. The ultimate truth about the hidden universe reveals that consciousness itself might be the rarest and most precious phenomenon in a cosmos dominated by invisible forces and substances that dwarf ordinary matter by ratios that exceed human imagination. The convergence of evidence from cosmic microwave background observations, supernova distance measurements, galaxy rotation curves, Gravitational lensing surveys and Big Bang nucleosynthesis calculations all points to the same inescapable conclusion. Ordinary matter, the protons, neutrons, and electrons that form atoms, molecules, stars, planets, and living beings, comprises only 4.9% of the universe's total energy content. This means that everything familiar to human experience, everything that interacts electromagnetically, everything that can emit, absorb, or scatter light, everything that participates in chemistry and biology, represents less than 1/20th of cosmic reality. The atoms in your body, the stars in the sky, the galaxies stretching across space, all of it combined is vastly outweighed by invisible components that remain forever hidden from direct observation. Dr. Sean Carroll's research on the foundations of cosmology suggests that this distribution isn't accidental, but might reflect fundamental features of how complexity and organization emerge in the universe. The small fraction of matter that can participate in electromagnetic interactions might be precisely the fraction required to form the complex structures necessary for chemistry, biology, and ultimately consciousness. If this interpretation is correct, then conscious observers like humans exist at the interface between visible and dark reality beings, composed of the rare matter that can organize into complex patterns while embedded within a universe dominated by substances that cannot form stars, planets, or life itself. Consciousness might be possible only in cosmic regions where ordinary matter creates islands of complexity within oceans of dark matter and dark energy. The anthropic principle provides a framework for understanding why conscious observers find themselves in a universe with this particular composition. Dr. Brandon Carter's reasoning suggests that universes with different ratios of ordinary matter, dark matter, and dark energy would either collapse too quickly, expand too rapidly, or fail to form the structures necessary for conscious observers to evolve. From this anthropic perspective, the 4% of ordinary matter isn't a cosmic accident, but represents the optimal fraction for supporting conscious observation. More ordinary matter would create a universe that collapses before life can evolve. Less ordinary matter would create a universe where galaxies, stars, and planets cannot form. The observed composition might be precisely fine-tuned to maximize the probability that conscious beings will emerge to study cosmic composition. Recent research in astrobiology and complexity theory supports this interpretation by showing that consciousness requires extraordinarily precise conditions spanning dozens of orders of magnitude in energy, time, and spatial scales. Dr. Paul Davies's research on the emergence of life demonstrates that biological complexity depends on stable chemical environments that can only exist in cosmic regions where electromagnetic forces dominate over gravitational collapse and cosmic expansion. The hidden 96% of the universe creates the cosmic scaffolding that makes these stable environments possible. Dark matter provides the gravitational framework that allows galaxies to form and persist for billions of years. Dark energy ensures that cosmic expansion continues at rates that permit stellar evolution and planetary formation without triggering immediate cosmic collapse or runaway expansion. Without dark matter, galaxies would not have sufficient gravity to maintain stable stellar populations over the timescales required for biological evolution. Without dark energy, the universe would either recollapse before life could emerge or expand so rapidly that gravitational collapse could never overcome cosmic expansion to form any structures at all. Dr. Max Tegmark's research on cosmic habitability zones suggests that conscious observers can only exist in cosmic environments where all three components, ordinary matter, dark matter, and dark energy, maintain precisely the ratios observed in our universe. This creates what cosmologists call the cosmic habitable zone, regions of space and time where conscious observation becomes possible. The mathematical precision required for this cosmic habitability is extraordinary. If dark energy were stronger by just a factor of 2, cosmic acceleration would prevent galaxy formation entirely. If dark matter were less abundant by a factor of 3, galaxy clusters would not provide the gravitational wells necessary for efficient star formation. If ordinary matter were more abundant by a factor of 10, the universe would collapse before stars could synthesize the heavy elements required for planetary chemistry. This precision suggests that conscious observers exist at an incredibly narrow intersection of cosmic parameter space, where complexity, stability, and information processing can coexist for the billions of years required for evolution to produce beings capable of contemplating their own cosmic context. Recent developments in information theory and consciousness research provide additional insight into why ordinary matter might be the critical component for conscious observation. Dr. David Chalmers' work on the hard problem of consciousness suggests that conscious awareness might depend on specific types of information integration that are only possible through electromagnetic interactions between charged particles. If consciousness requires electromagnetic field effects, neural networks based on ionic currents, and biochemical processes involving molecular recognition, then conscious beings could only emerge from the small fraction of cosmic matter capable of participating in electromagnetic interactions. Dark matter and dark energy, which interact only gravitationally, might be inherently incapable of organizing into the complex information processing structures required for conscious awareness. From this perspective, the 4% of ordinary matter represents not just the visible portion of the cosmos, but the conscious portion, the fraction of cosmic reality capable of contemplating its own existence and wondering about the nature of the hidden 96% that surrounds it. The ultimate truth about cosmic composition might be that consciousness naturally emerges at the boundary between visible and dark reality, requiring both components to create the stable, complex environments where conscious observation becomes possible. Consciousness exists because ordinary matter creates complexity within a cosmic framework dominated by dark components. Dr. John Wheeler's concept of the participatory universe suggests that consciousness plays a fundamental role in determining the nature of physical reality through the process of observation. If this interpretation is correct, then the existence of conscious observers might actually influence the cosmic composition they observe, creating a kind of cosmic feedback loop between consciousness and cosmic parameters. Recent research in quantum cosmology explores whether consciousness might participate in cosmic evolution through quantum measurement effects that extend across cosmic scales. Dr. Andre Lin's research on quantum cosmology suggests that conscious observation might play a role in determining which branches of cosmic evolution become actualized from the quantum multiverse of possibilities. If consciousness participates in cosmic evolution, then the observed composition of ordinary matter, and dark energy might not be independent of the existence of conscious observers. The universe might naturally evolve toward states that support conscious observation, creating anthropic selection effects that ensure conscious beings always find themselves in cosmos with compositions that permit their existence. The implications of this ultimate truth extend far beyond cosmology to fundamental questions about the purpose and meaning of conscious existence in a universe dominated by invisible components. If conscious observers represent the universe's mechanism for understanding itself, then consciousness might be the most important phenomenon in cosmic evolution despite being based on the rarest forms of matter and energy. Dr. Freeman Dyson's research on cosmic evolution suggests that consciousness might be the universe's method for processing information about its own structure and evolution. From this perspective, conscious observers serve as cosmic sensors that gather and integrate information about cosmic composition, providing feedback that might influence future cosmic development. Recent research in digital physics and computational cosmology explores whether the universe itself might be a vast information processing system where consciousness represents specialized subsystems designed to understand and potentially influence cosmic evolution. Dr. Stephen Wolfram's investigations of computational cosmology suggest that conscious observation might be necessary for cosmic computation to achieve certain types of complex calculations.